Imagine waking up, grabbing your morning coffee and checking your phone, only to realize the car sitting in your driveway didn't just, cost you money yesterday.
Right.
It actually generated a profit while you slept. Like trading electricity like a high-frequency Wall Street broker.
I mean, it sounds like complete science fiction, right? But
Yeah.
the physical and digital infrastructure to actually make that happen is actively being built right now.
Wow.
Yeah, the vehicle is shifting from this closed, purely mechanical loop into an open node on the global energy and data grid.
And if you're joining us today as a learner, you already know we are in the middle of a massive technological realignment.
Absolutely.
But the headlines rarely capture the sheer mind-bending complexity of what is actually happening beneath the sheet metal. So our mission for today's deep dive is to explore how the electric vehicle is being completely rewired.
From the ground up, basically.
Exactly. We are going down to the bare metal.
Sure.
From the massive shift in software architecture inside the dashboard to the physical laws of alternating current dictating the plug. And then, the thermal limits of the transformers on your street, the giant gigawatt battery facilities buffering the whole system, and finally, the fierce political battles determining who actually pays for all of this.
It's a lot.
It is a lot. Okay, let's unpack this. Because before a modern EV even draws a single watt from the physical world, its entire internal logic has been, fundamentally transformed.
Yeah, we are basically looking at the death of the legacy automotive architecture. I mean, historically, a vehicle might have had up to 100 isolated electronic control units.
Wait, 100? Just scattered throughout the car?
Scattered everywhere throughout the chassis. You'd have one module that just handles the anti-lock brakes. Then a completely separate module controls the climate. Another one handles the infotainment.
Oh, I see.
And they were these hard-coded, low-compute silos operating almost entirely independently of each other.
It sounds like a massively inefficient bureaucratic committee where, none of the departments are allowed to speak to each other.
That is exactly what it was, a very heavy, very rigid committee. But the industry has pivoted hard toward Level 4 and Level 5 software-defined ecosystems.
Okay. Software-defined ecosystems, so SDVs.
Right, SDVs. Automakers are tearing out that distributed mess and replacing it with a centralized zonal compute architecture.
Meaning fewer computers doing more work.
Exactly. You have a few incredibly powerful AI-driven core processors that act as a unified brain. They take in massive amounts of telemetry in real time.
Wow.
We're talking about terabytes of data, analyzing battery cell degradation, ambient weather, driver behavior, and sensor fusion, all simultaneously.
So, the transition isn't just swapping a gas tank for a battery pack. It sounds like we're transitioning from cars being like old flip phones with a few hardwired buttons to cars being smartphones on wheels.
That's the perfect analogy. And it fundamentally changes the business model.
Right, because it opens up a massive new revenue stream.
Yeah.
I saw the projections showing software and electronics revenue in the industry growing from, I think it was roughly $80 to $100 billion today.
Yeah, that's the current estimate.
And it's projected to hit upwards of $250 billion by 2030, with some models even projecting $1 trillion by 2034. That is insane.
It's staggering, and it's because the profit pool is shifting from just the point of sale to the entire life cycle of the vehicle.
Oh, so making money long after the car leaves the lot.
Precisely. Take AI-driven predictive maintenance, for example. Because this centralized architecture monitors everything down to the millivolt variance in a specific battery cell.
Right.
The system can actually predict a hardware failure weeks before it physically happens.
Oh, way.
Yeah, fleet operators are already seeing maintenance costs drop by up to 40%.
Wow.
And their vehicle uptime is improving by 20%. And on the consumer side, automakers are heavily leveraging over-the-air updates to monetize things like ADS, advanced driver assistance packages, or even unlocking extra battery capacity or tweaking suspension dynamics on demand.
See, I have to push back on the consumer side of that model, though. As a buyer, the friction there is immense. Am I really expected to pay a monthly subscription to activate heated seats?
I know, it sounds crazy.
Or like highway assist cameras on a piece of hardware I already purchased in full. It feels like buying a house and the builder charging me a monthly access fee to use the front door.
What's fascinating here is that the automakers who actually survive this transition are the ones who realize that extortionate monetization will destroy their brand equity.
Right. Consumers will just walk away.
Exactly. For this software-defined model to succeed, OEMs have to deliver continuous, tangible value.
So not just a random paywall for dormant hardware.
No, it has to be a dynamic service. Things like machine learning algorithms that drastically improve your localized autonomous routing over time.
Okay, that makes sense.
Or proactive failure mitigation that saves you a stressful trip to the dealership. The software has to actively earn its keep to maintain that long-term customer retention.
Okay, but all that continuous data processing and AI computation requires serious wattage, which brings us to the physical reality of powering these rolling supercomputers.
Oh, definitely.
Because the digital architecture might be unified globally, but the physical act of charging them is totally fractured, depending on whether you're parked in, say, Chicago or Munich.
Yeah, the software dreams of a borderless world, but the hardware is completely beholden to the historical legacy of the 20th century power grid.
Right, and the roots of this go all the way back to the 1800s. The U.S. grid is essentially a byproduct of the Edison and Westinghouse era, standardizing on a 120 and 240-volt single-phase system running at 60 hertz.
Right, 60 hertz.
But Europe, meanwhile, completely rebuilt its power infrastructure after the Second World War. So they converged on a much beefier 230-volt single-phase and 400-volt three-phase system operating at 50 hertz.
And those foundational grid differences completely dictated the physical interface.
The plug itself.
Exactly. Europe mandates the Type-T Menikes connector for AC charging, specifically to handle that three-phase power, and they use CCS2 for DC fast charging under their AFI regulations.
But North America went a different route.
Yeah, North America relied on J1772 and CCS1 for years. But now, they're in the middle of a massive convergence onto the SAE J3400 standard.
Which is basically the official name for Tesla's NACS connector, right?
Correct. Formerly Tesla's proprietary NACS connector.
Wait, so even if an automaker spends $1 billion developing a quote-unquote global car-like same chassis, same motor, same LFP battery chemistry, they physically can't just slap a universal charging port on it.
They absolutely cannot.
The guts of the car have to be fundamentally different.
If we connect this to the bigger picture, you realize that a truly global EV is basically an engineering myth.
Wow, really?
Yeah. The onboard charger, the OBC, which is responsible for rectifying the grid's AC power into DC power to pack into the battery, is bound by strict laws of physics.
Okay, how so?
Well, if you design an OBC transformer for a 60 hertz American grid, and then you try to feed it 50 hertz European power, you encounter a phenomenon called magnetic core saturation.
Oh, because the frequency is slower in Europe, so the voltage is applied for a slightly longer duration during each cycle.
Precisely. And that longer duration pushes the magnetic flux density inside the transformer beyond its physical limits.
So what happens then?
The core saturates, the efficiency just plummets, and all that excess energy converts directly into heat.
Yikes.
Yeah, you would literally degrade the insulation and fry the printed circuit boards. So automakers are forced to design, test, and manufacture completely localized OBC firmware, transformers, and cooling systems for different continents.
And that's just the physical power side. I imagine the regulations don't help either.
Not at all. Add in the differing homologation laws like FMVSS in the US versus UNECE safety standards in Europe, and the manufacturing complexity is staggering.
So the engineers solve the frequency and voltage puzzle inside the car so it doesn't physically melt. But then you face the macro-level physics of where to actually plug that car in. Because a recent study uploaded to the ArcSIF database by Biswar Mukherjee reveals something wild.
Oh, that study is fascinating.
Right. Finding the cheapest place to build a charging station is mathematically the worst possible thing you could do to the local power grid.
Yeah, the Mukherjee study is a brilliant look at the clash between financial optimization and electrical reality.
Because when planners try to save money, they just clump things together.
Exactly. When infrastructure planners or private companies map out a new charging network, their primary directive is almost always minimizing upfront CapEx capital expenditure.
Right. They want to trench less conduit, buy fewer parcels of land, and, just streamline the permitting process.
So they naturally cluster high-power, multi-port fast chargers together at a handful of major commercial nodes.
Here's where it gets really interesting. If I'm a city planner, the smart financial move is putting one massive multi-port charging station downtown to save money.
Financially, it's highly efficient.
But you're saying that's like putting every single restaurant in the city on one block. It just creates a massive traffic jam, but for electricity.
That is spot on. It creates an absolute nightmare for the local distribution grid. The study analyzed localized loading intensities and found that clustering chargers pushes nodes past 0.25 to 0.30 per unit loads.
Let's break down that per unit metric for a second, because that's the threshold where the physical infrastructure actually starts to buckle, right?
Right. In power systems, the per unit system expresses the load as a fraction of the base capacity of the equipment, like a neighborhood transformer.
Okay.
Transformers are thermally rated based on the assumption of intermittent diverse loads. You know, a neighborhood full of houses has air conditioners turning on and off at different times. They cycle.
We aren't all drawing max power all the time.
Exactly. But a cluster of 350 kilowatt DC fast chargers running at high utilization draws a massive sustained load.
So the transformer just cooks.
Pretty much. The transformer oil never gets a chance to cool down. The internal insulation degrades rapidly, which drastically shortens the lifespan of the equipment or causes an outright failure.
Wow. Planning frameworks that prioritize minimal investment basically ruin service reliability.
Yeah. The data in the study bears that out perfectly. Mukherjee demonstrated that if you take that exact same aggregate charging capacity,
The same total kilowatts.
yes, the exact same amount, and you distribute it uniformly across the grid rather than clustering it, the system's operational performance improves dramatically.
Just by spreading it out.
Yes. Uniform distribution reduces the energy shortfall, which is the unmet charging demand, by up to 74% for vehicle fleets utilizing 20 kilowatt-hour batteries.
74%. That's a massive operational gain just by changing the geographic layout.
And it drops the shortfall by 73.5% for larger 40 kilowatt-hour fleets.
That's incredible.
Yeah.
But the study also points out that as batteries get larger, the nature of the charging constraint fundamentally changes, right?
Yeah, we are shifting from a port-limited regime to a power-constrained regime.
Meaning what? Exactly.
Well, when the market was dominated by early EVs with small batteries, consumers just needed physical access to a plug. A standard level 2 AC charger could fill the battery while they were at work.
So they were port limited. They just needed an open spot.
Right. But today, with 80 or 100 kilowatt-hour packs becoming common, AC charging simply cannot deliver enough energy during a typical dwell time to meaningfully recharge the vehicle.
The battery is just too big.
Exactly. The limiting factor is no longer the plug. It's the raw flow of high-voltage power. Fast charging is mandatory for quick turnaround times, which only exacerbates those severe transformer bottlenecks if the stations are clustered.
Okay, so if uniform distribution isn't always geographically possible, and centralized clustering threatens to literally melt the local transformers, the grid needs a buffer.
It desperately needs a buffer.
It needs a way to decouple the immediate demand of the vehicles from the real-time generation of the power plant.
Which is exactly why the automotive industry is aggressively pivoting into the utility-scale energy storage business. You cannot successfully deploy millions of SDVs if the macro environment collapses every time people plug them in after work.
Which completely recontextualizes that massive $4.3 billion agreement between Tesla and South Korea's LG Energy Solution.
Absolutely.
They are spinning up a retooled facility in Lansing, Michigan, which, interestingly, used to be a GM joint venture to produce these lithium iron phosphate, or LFP, prismatic cells.
Right. But the key here is that none of those batteries are going into cars.
Really, none of them.
Not a single one. They are entirely dedicated to stationary energy storage, specifically Tesla's Megapack systems.
Oh, wow.
And LFP is the ideal chemistry for this application. You don't care about the energy density or the physical weight because the battery isn't moving.
Right, it's just sitting on the ground.
Exactly. What you care about is thermal stability, incredibly high cycle life, and cost efficiency.
So Tesla, the quintessential car company, is acting like a giant sponge for the national grid. Is this energy storage business becoming the main event rather than a side hustle?
It's certainly a massive pillar of their strategy now, and it reflects a broader industry trend. Automakers are investing in domestic battery production, not just for the cars, but to ensure the grid can actually support the electrification shift.
So these megapacks act like massive hydroelectric dams for the power grid. They capture excess renewable energy when solar and wind production peaks during the day.
Right.
Hold it in a reservoir and then release it exactly when those localized fast-charging bottlenecks demand it.
It's a strategy of peak shaving and energy arbitrage. By deploying these utility-scale batteries at the site of the chargers or at local substations, you flatten the demand curve.
So the transformer sees a smooth, manageable load.
Exactly, while the vehicles still get their high-power burst.
It is stunning to see how lucrative that buffer has actually become. Tesla generated $12.8 billion from their energy segment last year alone.
Yeah, the numbers are huge.
That's 13% of their total revenue, growing at 27% year over year. It's providing massive top-line support even when their core automotive deliveries faced headwinds. They aren't just an OEM anymore. They are a decentralized utility provider.
The strategic moat of the 21st century for automakers isn't just manufacturing a great chassis anymore. It's securing the localized power grid so the customer experience doesn't degrade.
But securing that grid, overhauling thousands of transformers, building gigawatt battery facilities, and writing billions of lines of code, it all requires a staggering amount of capital.
Staggering.
Which brings us to our final piece, the intense political and legal battle over how this transition is funded and regulated. Because rebuilding the national grid isn't cheap.
No, it's not. The physics of alternating current and the realities of capital markets are ultimately governed by federal and state policy. And right now, that policy is highly volatile.
Very volatile. At the federal level, we are watching a massive legal clash over the $5 billion National Electric Vehicle Infrastructure Program, or NEVIA.
Right, NEVI.
The stated goal of that was to build out a seamless, fast-charging network along the nation's highway corridors.
But the deployment has been contentious. The Trump administration initiated a pause on the NEV program to execute a comprehensive review.
Right.
Their priority was overhauling the guidance to heavily emphasize cost efficiency, safety protocols, and technological innovation.
Basically requiring states to pause deployment and resubmit their action plans under these new metrics.
Correct, which triggered a massive lawsuit from 20 states and the District of Columbia.
And U.S. District Judge Tana Lin ultimately ruled that the administration's pause was unlawful. She actually stated that they improperly yanked the NEVI formula program's cord out of the outlet.
Yeah, arguing that the sudden freeze violated the Administrative Procedure Act.
Because they acted capriciously without proper transitional off-ramps.
Exactly. But in response, Transportation Secretary Sean Duffy defended the administration's strategic pause. He relied heavily on the deployment data to make his case.
What did the data show?
He noted that once the new streamlined guidance was actually implemented, the DOT managed to obligate 39% more NEVI funds to the states in just 5 months than the previous administration had obligated in 3 full years.
So while the federal apparatus is locked in this battle over the speed and the mechanics of deployment, the states are left to chart their own course.
They are on their own, yeah.
And especially after the repeal of the Biden-era One Big Beautiful Bill, which, stripped away those federal EV tax credits, the state-level response has aggressively polarized.
We are literally watching the decentralization of transportation policy in real time. Without a unified federal subsidy, states are leveraging their own treasuries and legislative powers, creating vastly different market conditions.
In Democratic-led states, the legislative focus is on aggressive market acceleration to hit climate targets. For example, Washington State passed SB 6354, and Hawaii passed HB 2030.
Right, and both of those bypass complex tax rebates in favor of instant point-of-sale cash discounts at the dealership.
Just immediately lowering the barrier to entry for the consumer.
Exactly. Meanwhile, states like New York with SB 801 and Minnesota with HF 1139 have bypassed the dealership entirely.
Oh, by rewriting the building codes.
Yes. They passed laws mandating that all new residential and commercial construction is fundamentally EV-ready with pre-installed heavy conduit.
Conversely, Republican-led states are passing legislation heavily focused on market neutrality and preserving traditional infrastructure funding mechanisms.
Yeah, completely different approach.
Like West Virginia passed HB 912 and Tennessee passed SB 2644. These are strict freedom of choice bills that legally preempt any state or local agency from banning the sale of internal combustion engines.
They are actively protecting gas-powered ICE vehicles.
And they are tackling the highway funding gap head-on. Because EVs obviously bypass the traditional gas tax that pays for road maintenance, Kansas and Missouri have implemented heavy EV registration fees.
Right, Kansas HB 2003 and Missouri HB 2609.
Exactly. Alongside new per-kilowatt-hour excise taxes on public fast charging to ensure the highway trust funds remain solvent.
So they're replacing the lost gas tax revenue.
So what does this all mean? We have some states rewriting real estate codes to mandate chargers and handing out cash, while neighboring states are legally protecting the combustion engine and taxing the electrons flowing into the batteries. It looks like we are essentially building 2 completely different transportation ecosystems within the exact same country.
This raises an important question, right? Navigating a patchwork of 50 different micromarkets, each with completely different incentives, building codes, and taxation structures make centralized product planning incredibly difficult for the automakers.
It must be a nightmare.
With federal policy shifting, state lawmakers have essentially become the primary architects of the transportation sector. They are the ones balancing climate goals and technology innovation with market pragmatism and infrastructure funding.
It's a phenomenal puzzle to watch unfold. So for you listening, transitioning to electric mobility is so far beyond just swapping out an engine for a battery pack.
It's an entire systemic overhaul.
Exactly. It requires rewriting the fundamental software architecture into a unified AI brain. It demands re-engineering the internal physics of the vehicle to match century-old, localized power grids. It requires solving the mathematical constraints of charger placement to prevent thermal meltdowns in neighborhood transformers. It relies on multi-billion-dollar gigawatt battery facilities to act as grid-scale dams.
And all while navigating a labyrinth of deeply fractured state and federal policies.
Right.
It is arguably the most complex synchronization of digital software, physical infrastructure, and macroeconomics in modern industrial history.
Which brings us back to where we started, a completely mind-bending idea to leave you with. If these vehicles are now brilliant software-defined computers, and they are physically integrated into a grid that is being buffered by massive battery storage systems, what happens when millions of these AI-driven cars begin talking to the grid autonomously?
That's the billion-dollar question.
Imagine a near future where your vehicle's neural net continually analyzes localized wholesale electricity pricing. It could automatically draw power from the grid at 2 a.m. when high wind production drives the price to fractions of a cent.
Storing it in the battery while you sleep.
Exactly. And then it automatically discharges and sells that power back to the grid during an air conditioning spike at 5 p.m.
Buying low, selling high.
Yes. Your average commuter vehicle fundamentally transforms into the most active day trader on the global energy market, trading wattage while it just sits in the garage.
The closed mechanical loop is completely gone. The vehicle is now an active participant in the wider ecosystem.
An open, digital, highly lucrative ecosystem. Thank you for joining us on this deep dive. Keep questioning, keep exploring, and we will see you next time.